Today we will discuss some problems on mass diffusion, or more specifically on diffusion in solids. And I will discuss some typical problems that you will encounter in undergraduate teaching, or at undergraduate level more specifically. Okay. So, we will start with a problem on steady state diffusion, and then we will go to unsteady state, talk about unsteady state diffusion in solids. Now, you know the phenomenological description of diffusion in solids, and where we write the flux of a species I along x direction, popular Fick's law, C of y. One dimensional Cartesian coordinate system. So, this is the x direction, and we know that this could be, depending on in which unit you use express C, we can have mass flux or molar flux. Okay. As I said in the first lecture, you must be conversant with the dimensions of the flux as well as the diffusion coefficient, just like various parameters that we encounter while solving problems in process metallurgy. And if you apply this Fick's law and perform a material balance, and in 1D constant property, steady 1D constant property, you have the limiting form of the Laplace equation, that is we write that is what is boils down to. Okay. And in 3-dimensional, or you know that we write in heat transfer and in mass transfer. So, conduction and diffusion are basically essentially, one is thermal diffusion, the other is mass diffusion. They are governed by the same type of, there is one-to-one similarity between Fourier's law as well as Fick's law. So, the solution to this equation is that we have concentration given in terms of C, which is a function of x, is given in terms of two constants, alpha and beta, and these two constants are dictated by the boundary conditions here, C1 and C2, and the diffusion is this particular direction. So, with these words, let me quickly pose a problem, and this is a typical class of problem which you will encounter in the context of steady state diffusion, which he calls a permeation of a gas through metal. So, for example, you may have a container, that container may be containing a copper container, and you may have inside pressurized hydrogen, and the hydrogen can diffuse and escape from the container to the ambient. So, that is basically permeation of hydrogen through copper, which is the vessel lining. In this case, we will pose the problem like this, that we have a gas passage where we have a thin film, and this is a film of platinum. And what is this? The width of the thickness is half a millimeter thickness, that is what it is. And the area here, area foil, is actually, if you see it perpendicular to the board, this is the rectangular area, that is what we are talking about, through which, and it is given as 0.1 into 0.15. So, one side is 10 centimeter, the other side is 15 centimeter. So, this is equal to 15 into 10 to the power minus 3 meter square, that is the area. On this side we have hydrogen gas, that is at 3 atmosphere pressure. On this side we have hydrogen gas, that is at 0.5 atmosphere pressure. And there is a natural tendency for hydrogen to permeate through the platinum foil, and we want to calculate the rate of permeation given that diffusion coefficient of hydrogen through platinum is, the value is 6 into 10 to the power minus 9 meter square per second, and the Sievert's law constant is also given, because hydrogen as gas will not transpose that we know, transfer that we know from our theory. So, the hydrogen, this reaction takes place at the interface, and then the monoatomic hydrogen diffuses through the foil, and this reaction is assumed to be in equilibrium because the rate of hydrogen transport is assumed to be in this particular problem diffusion controlled. So, the chemical reaction is virtually at equilibrium. So, therefore, and it is a diatomic gas, we apply our thermodynamics. So, we know it will dissolve into platinum, okay, and this reaction will take place in accordance with the Sievert's law, and that reaction can be assumed to be at equilibrium. So, the Sievert's law constant is given as 0.07 centimeter cube of hydrogen per gram of nickel, per gram of platinum, per atmosphere raised to the power half. That is the unit of Sievert's law. And this is, when you talk of volume, this is given as STP. And the gram of nickel can be converted into the volume of nickel by using the density of nickel, for example. Similarly, this volume of hydrogen gas can be converted into corresponding gram mole by assuming ideal gas behavior. So, this juggling you should be very quickly able to do during exams, or when you are solving the problems. So, that, as I said in the beginning itself, that you cannot substitute the parameters as such, because the left hand side and the right hand side has to be of an equation has to be dimensionally consistent. So, therefore, now if you look at this equation, the solution of this equation gives us that the net rate of transport of a species I, the consequence of this equation, okay, is this is equal to the diffusion coefficient of I multiplied by area divided by the path of diffusion through which it goes, and then we say that this is the equilibrium constant multiplied by, when in the context of a gas diffusion, we will say it is P of I, okay, at 1 minus P of I at 2, in which K times square root of P of I essentially represents the concentration, K times square root of Pi2 essentially represents the concentration here itself. So, this is what is the Sievert's law constant. You will sometimes find that you may be asked to calculate, or given this particular product, which is also termed as the permeability and denoted by a capital pi, with a capital pi. Okay? So, the permeability may be given in terms of temperature, etc. So, you should be able to isolate that. This is, sorry, not A into K, I will write D into K, diffusion coefficient into, that is called the permeability. I stand corrected. So, do not get scared, if the data is provided to you, not specifically in terms of diffusion coefficient and the Sievert's law constant, but given as a combined variable known as the permeability. So, you know that it is the product of the two parameters which have been given to you. So, now we can very easily write down that what is the value here, and in this particular case we will see that if you substitute the value, okay, let us convert that the Sievert's law constant. So, k is equal to 0.07, okay, and we have, if we multiply it by divided by, actually this figure, if we apply the ideal gas law, this will come out to be, this is the value, we know that at NTP, we have 22.400 cc corresponds to 1 gram mole, okay, but this is STP. So, this value will come out to be 399. So, but I have not written that, for the sake of simplicity I have assumed this to be 2204. So, and then you multiply it by 10 to the power 6 conversion of centimeter cube to meter cube, and then you multiply it by the density of platinum, okay, and the density of platinum is I do not have the value, I have, I think I have worked it out with density of nickel actually. So, that is 8.9 grams. So, let us say that. So, this value needs to be substituted. I do not remember the value here. So, this is actually I have substituted, I have worked it out with 8.9, but you should use the correct density value, okay. And if you take the density to be 8.9 for the moment, so this is the rho platinum, that is what it should be. So, that I would say rho platinum, that is the density. Let me not put the wrong value, okay. And then you should be able to find out that this is actually 0.07 multiplied by 10 to the power 4 divided by 224 into 4 platinum. So, that is, and what should be the unit of this? You should be able to write now. This is in the unit of gram mole per meter cube atmosphere raised to the power half. Now, if you look at it here, for example, your area is meter square, diffusion coefficient is meter square, L is meter. So, you have a meter cube. So, that meter cube and this meter cube will cancel. This atmosphere raised to the power half with this atmosphere raised to the power half will cancel out. What you are going to left with is gram mole by second, and that second coming from the diffusion coefficient. So, if you, so this should be now, if you substitute K in this unit, okay, and this should come out to be in gram mole per second. So, the conversion of the given unit to this particular, so we have a, this is given 0.07 which is written here, and I have centimeter cube to meter cube, I have multiplied it by 10 to the power 6, and this is the conversion of volume at STP to gram mole, and then we have to multiply it by density because to get a meter cube, and then we get, this is the final dimension of the whole thing that you can get. So, if you substitute the values here, so you will put Ni is equal to area, so which is equal to 15 into 10 to the power minus 3 multiplied by diffusion coefficient, which is given to be 6 into 10 to the power minus 9. Okay. So, this is meter square, this is meter square per second, and this is 5 into 10 to the power minus 4 meter. Okay. And then we have 1.732, that is the, and this is 707. So, square root of 0.5 is 0.707, square root of 3 is 1.73, and then you have a value which is equal to 0.07 multiplied by 10 to the power 4, okay, and then we have rho platinum and divided by 224. So, if you substitute the value here, or everything is known, and you will find out that this comes out to be roughly 1.7 into 10 to the power minus 11 gram mole. So, that is the net rate of permeation of hydrogen. Okay. So, please substitute the value if you here and check that whether you get the same value or not. Okay. So, I remember the final value, but I think I have substituted a wrong value for platinum density in my calculation. So, that is why I am not quoting. So, I am giving you the correct answer. This is if you substitute the value of rho platinum correctly, in that case you will get this value. Okay. So, that is the rate of permeation actually. Rate of permeation, and the whole thing is happening, these values are given, which is at 1000 degrees centigrade, everything is given. This is not a room temperature phenomena, this is a high temperature phenomena, and this high temperature phenomena tells us that we can consider this reaction to be taking place under equilibrium condition, because the rate of chemical reaction at high temperature is quite fast. So, this is steady state problems of diffusion are very straightforward. You have to just know the phenomenological description, the integrated form of the equations you must be able to know. Remember that n of I is equal to d of I multiplied by area divided by L path of diffusion into C1 minus C2. If you are so, this is the integrated form of the governing equation that I have written earlier, and you must be careful when you substitute the units. For example, if you are given units in weight percentage, for example, do not just substitute the weight percentage values here, C1 minus C2. Okay? So, weight percent needs to be converted, because this should come out to be, as I said, either in terms of mass per unit time or moles per unit time. That is the unit of net rate of transport. So, accordingly, be careful to substitute C1 and C2 in correct units, so that you do not make the mistake. So, with these words, now I will move on to an unsteady state problem. Okay. And unsteady state equations in one dimension, basically in Cartesian coordinate system, which we can write down as constant property. So, we will write down. So, y is the coordinate in which often it is said fixed second law. So, and there are a good deal of application of unsteady state diffusion, as you all know, to find out how much carbon has diffused into steel and so on and so forth. So, I will illustrate a problem where we will see the various components or various possible types of calculations that you may encounter in unsteady state diffusion phenomena. But before that, I would like to tell you that when I have written this equation in Cartesian coordinate system, I could write also this equation in cylindrical as well as spherical coordinate system. Okay? Only this parameter is going to be changing, either having a 1 by r term or having a 1 by r square term, depending on the coordinate system that you use. Now, once you write this governing equation, you have to specify that what is the boundary condition. So, you have one initial condition and then two boundary conditions. Okay? So, for all values of y, I can say 0 to L, and then at y is equal to 0 and at that y is equal to L. And what is the value of C? That needs to be specified. Notationally we use, and this we use as C is equal to the surface concentration. So, if you remember your metallurgical kinetics fundamentals, you must understand that when you are solving the diffusion process, the diffusion particularly when a species diffuses in the gas diffusion process, like for example carburization with the gaseous atmosphere, nitrogen diffusing into steel, etc. So, you will find that diffusion is preceded by a chemical reaction, which may be a dissolution reaction, which may be a chemical reaction. So, it is since we are trying to calculate the rate of diffusion, it essentially turns out the rate of other processes are infinitely fast or they are operating close to equilibrium. So, the chemical reactions associated with the diffusion process or the phenomena under consideration can be assumed to be at equilibrium, and it is based on that I have given an extensive lecture on this in my iron and steel making as well as transport phenomena, that the surface concentration is assumed to be fixed, where the solid carbon gets into dissolved carbon and that reaction is assumed to be at equilibrium, and you can find out from thermodynamics that what should be, given the temperature and pressure, what should be the surface concentration. So, that is a question we do not ask. We are solving the diffusion, so we must be having the boundary conditions specified to us. How we obtain the boundary conditions, okay, is particularly the surface boundary condition is a different issue altogether, which I assume that you know. Now, this we have two different geometries that we consider in Cartesian coordinate system. One is the slab geometry, and the slab geometry also, a finite slab geometry can also often be considered as a semi infinite geometry, as you all know, when this the one end of the domain can be considered to be physically at mathematically at infinity. So, if the diffusion species cannot penetrate too large a distance, because diffusivity d values are much smaller than the alpha values. Heat diffuses faster, mass does not diffuse fast, okay, that we all know. So, therefore, we can see that the concentration here is surface, and then for all time what happens is, no matter what is the time, these are different time values, and we see that it is not able to see this particular, it is not able to, the diffusing species is not able to penetrate, this is at a time infinity, okay, very long time it is not able to penetrate. So, therefore, the finite geometry can also be approximated as a semi infinite domain. So, in that case, if it is a semi infinite domain, so I will say that boundary condition will change, and I will say that at y tending to infinity or very large, then here I will say C is equal to Cs, and here I will say that the initial concentration will remain, the boundary conditions will change. Okay. So, now with this little background, let us pose a problem, and it is about diffusion of carbon in steel. Okay. Let us say that we have a slab geometry. We also know that if it is a semi infinite geometry, we will say we know for sure that the solution of the equation will yield the error function solution. Similarly, if it is a finite slab geometry, then we can conclude that an infinite series solution will come, as I have discussed in one of the lectures in the context of heat transfer. Thermal diffusion or heat conduction and mass diffusion phenomena are governed exactly by the same equation. You just substitute T by C and alpha by D everywhere, and you can repeat, you can get the same kind of a results. So, you do not have to learn the mass diffusion phenomena as far as mathematical treatment of the subject is concerned. So, T is to be interpreted as C and alpha is to be interpreted as D, and then the heat conduction theories can be translated on a one-to-one basis to corresponding mass diffusion phenomena. So, the problem is that we have temperature is given to be 900 degrees centigrade. It is a problem in which carbon is diffusing into steel. Carbon is diffusion in steel slab, and that slab has a width of 0.4 centimeter, 0.4 meter, 40 centimeter. Initially, as our carbon content of the sample was 0.1 weight percentage, and the surface concentration for all time is fixed at 1.2 weight percentage. The diffusion coefficient is given in terms of a d0 value and the corresponding activation energy value, and d0 is given to be 1.5 into 10 to the power minus 5 meter square per second, and activation energy of diffusion is given to be 142 kilojoules per mole. And we want to find out, there are several tasks. We want to find out, one, concentration of carbon. So, this will explain all types of possible numericals that you can get. So, that we are trying to address concentration at 1.5 into 10 to the power 4 seconds time, okay, of carbon. Where we want to find the concentration, we would like to say that y is equal to 0.3 mm. That is the distance at which we want to find a concentration. Okay. Second is, we want to find the penetration distance, at same time. We want to calculate the instantaneous flux, we want to calculate the time average flux, and we want to calculate number 5, the total amount of carbon, that has gone in, diffused into steel over 1.5. So, over this duration of time, how much of carbon has diffused into? These are the questions that we seek to answer on the basis of this data. Now, before the problem is given in terms of a slab geometry, now we can see that there is a L term here, okay, this is the actual domain length, and if you look at the dimension of d over t, this comes out to be meter square per second multiplied by second. So, this is meter square. So, this has a dimension of meter, and this distance is called the diffusion distance. Okay. So, if you divide L by square root d into t, so you say that 0.4 and diffusion coefficient. Now, on the basis of this, if you calculate diffusion coefficient, d is equal to d0 exponential minus q diffusion by RT, where T is equal to 1173 Kelvin. Okay. In that case, d0 comes out to be 6, d of carbon comes out to be 6 multiplied by 10 raised to the power minus 12 meter square per second. So, we put this value 6 multiplied by 10 raised to the power minus 12, time is 1.5 into 10 raised to the power 4 seconds. So, 6 into 5, 1.5 is 9. So, square root of 9 is going to be 3. So, this is going to be 0.4 divided by 3 multiplied by, this is 4. So, this is minus 8. So, minus 8 is minus 4. So, therefore, we can say that this comes out to be something like, say, much greater than 1. So, therefore, the diffusion distance is going to be only this much. So, therefore, even if you consider the slab geometry as half, if you take this value to be half, still it will come out to be 1. So, therefore, we can assume that the diffusing species does not see this interface within this time duration. So, therefore, we can apply the error function solution where we approximate the geometry to be a semi infinite geometry. It is also possible in this case to apply the infinite series solution, and you will see that the semi infinite geometry solution as well as the infinite solution will merge, practically merge, illustrating essentially that from either of the standpoints you should be able to address this particular point. So, having done this, I would now like to consider this finite slab geometry as a semi infinite geometry and start solving those particular questions that I have written on the right hand side. So, now concentration. So, we know the solution of the error function is, we have C, which is a function of y and t, is equal to C0 plus Cs minus C0 into 1 minus error function of y divided by square root of t. That is how the concentration profile is dictated. So, here it is C0 is 0.1, okay, and this is 1.2 minus 0.1. So, this is 1.1, and then we can say that this comes out to be 1 minus error function y, which is equal to 3 millimeter. So, it is 0.3 millimeter. So, 0.3 millimeter means 3 into 10 to the power minus 4, and then we have here what we have gotten is something like 0.4. So, square root of dt. So, this value comes out to be 2 times dt. So, this is 2, and square root of dt comes out to be, that we have already calculated here, okay, and that is 3 into 10 to the power 4. So, this value is actually error function of 0.5. So, that is what it is, error function of 0.5, and this one can get from the table, okay, error function tables are available, okay, and then you can say this is approximately is equal to 0.5, or more specifically I would say this is 0.52 or so on. So, therefore, we can say that the value will come out to be 0.1 plus 1.1 multiplied by 1 minus 0.52 is 0.48, and the answer is in this particular case 0.628 percentage. Let us look at the penetration distance at the same time. The penetration distance is nothing but 4 times square root dt. So, if you put y is equal to 4 times, then you get error function 2, and in that case what happens is this term becomes is equal to 0 and this becomes is equal to s. So, that is why it is 4 times square root dt is called the penetration distance. I hope you understood that if you put y is equal to 4 times 2 dt, 4 times square root dt will cancel out, 4 by 2 is 2, and error function of 2 is almost is equal to 1. So, this term will vanish, and therefore, C is going to be equal to C0. So, that means we say that we have been able to, we have reached a point where we got this initial concentration. So, that is the distance through which the diffusing species has been able to penetrate. Now, so for 4 times square root dt, so if square root dt comes out to be 3 into 10 to the power minus 4, so you can say the second part is nothing but 4 times of square root dt, and that is equal to 4 multiplied by square root of dt is 3 into 10 to the power minus 4 meter, and that is equal to 12, or 1.2 into 10 to the power minus 3 meter, or 1.2 millimeter. Let us calculate the instantaneous flux. To be able to determine the flux, you require to differentiate this term, differential coefficient of C with respect to y. So, therefore, you will know how to differentiate the error functions. because this is going to be 0, this will come out of the differential coefficient, and then you are going to have minus error function, differential coefficient of error function y over 2 square root dt with respect to y, how you differentiate. If you do, I am not going to show you that differentiation, that is done in the lecture itself, and if you do the differentiation in that case and substitute the surface condition, that is the flux at y is equal to 0, which is the surface, and then this comes out to be Cs minus C0 into square root d divided by pi t. Now, what is the unit here? The unit here is, if you want to get it in terms of kg per meter square per second, okay. In that case, this wet percentage value needs to be converted, because Cs and C0 are given in terms of the. So, we can now say that the instantaneous flux can be calculated as number 3 J of C at y is equal to 0 is equal to 1.2 wet percentage minus 1 wet percentage. So, this is 0.1 wet percentage, okay. And then we have the diffusion coefficient, okay. The diffusion coefficient we have calculated to be, I think, 6 multiplied by 10 raised to the power minus 12, and then the pi is the constant 3.142, and this is multiplied by the time that we have considered to be, and this flux is instantaneous. So, I would say this is equal to t is equal to 1.5 into 10 to the power minus 10 to the power 4 seconds. That is the time. Instantaneous flux at the surface y is equal to 0 and into 10 to the power 4. So, this is equal to, I would say, 1.1 wet percentage or 0.11, okay, and then I will multiply it by the density of steel, and that value is 7200, because it is diffusion of carbon into steel. So, I want to convert weight, this is weight fraction, kg of carbon in kg of steel, and that kg of steel is converted into meter cube, okay, by dividing it by 7200 kg per meter cube. So, now the 7200 appears in the numerator, and then we have this quantity comes out to be 1.12 if you take the square root multiplied by 10 raised to the power minus 4, okay. And then if you calculate this, 0.11 into 1.2 and then 1.12 10 to the power minus 4, 7200 and 0.1. There are 4 terms, 1, 2, 3, 4, yeah. So, and this is in kg per meter square per second, that is the term, okay. And if you do this calculation, then we can find out that this is nothing but 8.87 into 10 to the power minus 3 kg per meter square second. You should be able to now convert it to kg moles of carbon by divided simply with 12, and that should give you the instantaneous flux. The instantaneous flux and the time average fluxes are different by a factor of 2 only, okay. The time average flux means so this flux is at a time is equal to 10 to the power 4. You can imagine that the flux, as you know, it varies as inversely as time raised to the power half, okay. So, therefore, in the initial cases the flux is very rapid, and then the flux gradually decreases as the concentration curve. No? So, this is the line. So, you can imagine the slope is changing and decreasing as a function of time. So, the flux is going to be a function of time, and therefore, you know, you have to do a time averaging to find out that what is the average value of the flux, and that average value of the flux is nothing but 2 times J of C at y is equal to 0 and instantaneous. And so, therefore, this is equal to 17.7 into 10 to the power minus 3 kg per meter square per second. if the slab is given an area of area slab is also given. So, that I forgot to mention is 0.1 meter into 0.15 meter, and therefore, this is equal to 15 into 10 to the power minus 3 meter. Okay. And then we can see that we can, from this average value, we can calculate now the total rate of transport or total amount of carbon which is diffused into the system. So, the total rate of diffusion, total amount of carbon, and that is part 5, and total amount of carbon which is diffused into steel is equal to. So, this term we can say, we can represent this as J average, okay, Jc at y is equal to 0. That is the notation that we use, the time average flux with an overbar. Okay. So, we can take the value of Jc at y is equal to 0, and then if you multiply it by total time multiplied by total area, and that will give you Nc in kg. So, that is equal to 17.7 into 10 to the power minus 3 multiplied by 15 into 10 to the power minus 3, okay. And then we have the time which is equal to 1.5 into 10 to the power minus plus 4. So, this is total area and this is total time, and if you multiply these values, then we can find out this comes out to be approximately 3.98 kg of carbon. And what is the time? This time corresponds to roughly about 4 hours, approximately 4 hours. In 4 hours of time, only 4 kg of carbon has diffused into the system. Another problem that you find is given in terms of very common in the context of this semi-infinite diffusion in semi-infinite geometry is the relationship or the change in penetration distance with response to temperature. So, the material is same, time is same, but the diffusion is taking place at 2 different temperatures. Okay? In one case it may be 900, the other case it may be 1200 or 1300 degrees centigrade. So, you may be asked to compute the relative rate of penetration at corresponding to 2 different temperatures. So, in that context we will see that can say that suppose if I pose the problem as carbon diffusing in steel, okay, and what is given here is d0 which is equal to, in the last problem I have given the value of d0 and that d0 is equal to 1.5 into 10 to the power minus 5 meter square per second, and Q activation of diffusion is equal to 1.42 thousand kilojoules. (142 kilojoules or 142,000 joules per mole), and we are considering diffusion at 900 and 1300 degrees centigrade. So, 1173 Kelvin vis-a-vis 1573 Kelvin, and we have to find out that by what factor the penetration distance could change. So, we can see that the penetration distance L1p, so I would say L900 okay, penetration by L1300 penetration is equal to 4 times square root d900 into T divided by 4 times D 1300. So, therefore, this can be said to be D 900 by D. That is the relationship basically. And now, given this relationship, you should be able to first calculate that what is the value of D 0. Okay. So, diffusion coefficient at 900 should be 1.5 into 10 to the power minus 5 into exponential 142,000 divided by 8.314 into 1173, and D 1100 is equal to 1.5 into 10 to the power minus 5 exponential 142,000, this is minus of course, 142,000 divided by 8.314 into 13, sorry, this is 1573, not 1100, 1300. So, this is 1573. So, if you do take the ratio here, then what you find out is that this is going to be nothing but exponential e to the power half, and then we have 142,000 minus 142,000 divided by 8.314 into 1173, and this is going to be e to the power minus 142,000 okay, divided by 8.314 into 1573. And you can find out now that E of A divided by E of e to the power of B is equal to E A minus B. So, you should be able to evaluate this value and then find out that what is the final answer to the problem by increasing the temperature by what fraction the penetration distance really increases. And you can see that because it is related to square root of D and diffusion coefficient increases with temperature. Okay. So, we would expect the penetration distance also to increase with temperature, but not as strongly because it is square root of diffusion coefficient. So, you can find out this value very easily. And the last point before I think I have almost delivered the last part of the lecture. So, I think I want to I will take some more time. So, I think I do not have that much of time available today. So, I want to show you first the last thing about unsteady state diffusion is the unsteady state diffusion in a finite slab geometry, and in that context I will show you explicitly that the same problem that we have solved in the context of unsteady state heat conduction in a slab, if you remember. Okay, I have written an infinite series solution. The same will be applicable here also, and then we will solve a equivalent mass transfer or diffusion problem, and then we will for sure learn that if you know the physics or if you know the mathematical manipulation of governing equations and expressions in heat transfer, we should be able to apply the same fundamentals in the context of similar mass transfer phenomena also. That will be the subject matter of my next lecture.